neighboring group participation and also aromatic nucleophilic substitution reactions. So, first of all, neighboring group participation NGP. So, NGP, it is very important topic all entrance examination point of view. So, this neighboring group participation mainly it is this is nothing but SN-NGP. SN-NGP, this is nothing but nucleophilic substitution neighboring group participation. In neighboring group participation, actually what is the required condition where neighboring group participation takes place? So, in neighboring group participation, mainly the essential condition is presence of hetero atom at beta carbon. That means here we need internal nucleophile. And here, and the next one is here the concentration of external nucleophile is less than here this is neighboring group participation, that is presence of heteroatom at beta carbon is required, and that means this is this required internal nucleophile, and the concentration of external nucleophile must be less than the concentration of reactant. And here one more condition, here leaving group must be present antiposition to the leaving group must be present antiposition to the internal nucleophile. Here, so in this reaction, that is neighboring group participation, presence of heteroatom at the beta carbon is required, that is concentration of external nucleophile is less than the concentration of reactant, and leaving group must be present antiposition to the internal nucleophile. Now, let us discuss that is examples. So, where neighboring group participation takes place, that we are going to discuss that one. So, generally this neighboring group participation takes place in so many compounds, that is sulfur containing nucleophiles, nitrogen containing nucleophiles, and esters and other compounds are also possible. First of all, that is case 1. In case 1, that is nitrogen acts as a nucleophile. If you take example, that is CH3, here it is N, and here it is CH2, this is here it is H, this is CH2Cl. If it is treated with aqueous NaOH, what happens? This is CH3, here N, this is CH2OH. Mechanism, this is CH3, this is nitrogen, here it is CH2Cl. Nitrogen is having lone pair, this lone pair attacks from this side and loss of Cl minus takes place. This is CH3, this is CH3, here it is N, this is N, and here this is nitrogen, and next one it is CH2, this is CH2, this one is formed. And after the formation of this cyclic intermediate, here it is having hydrogen, this also having hydrogen, here this is already having hydrogen, this is plus charge. Now, the next one, that is a nucleophile, this OH minus may attack from this side, or OH minus may attack from this side. If it attacks here, this ring cleavage takes place. If it attacks here, ring cleavage takes place here. What we get? This is CH3, this is NH, here it is CH2OH. So, this compound is formed here, this hydrogen is present, this is also hydrogen is present. This is the example of neighboring group participation. This nitrogen, internal nitrogen acts as a nucleophile. So, this is neighboring group participation, case 1 by using nitrogen. After this one, next one, case 2. In case 2, that is sulfur acting as a nucleophile. So, this is case 2. In case 2, sulfur acts as a nucleophile. Sulfur acts as a nucleophile. Let us take example CH3S CH2Cl, and if you take CH3 CH2 here it is CH2Cl. In these two examples, sir, which is more reactive towards nucleophilic substitution reaction? Suppose both compounds are treated with aqueous 𝗂𝗧. Here also treated with aqueous 𝗂𝗧. This one also treated with aqueous 𝗂𝗧. So here this is treated with aqueous 𝗂𝗧, that is also treated with aqueous 𝗂𝗧. So here we get this product, this is CH3 SCH2OH. Here we get this is CH3 CH2OH. So the reactivity of this compound, it is greater than this compound. Here nearly 1000 times faster than this compound is nearly 1000 times faster than this reaction. Sir, both are same compounds, but it undergoes very fast, where it undergoes very slow. So why it is undergoes very fast? This is due to neighboring group participation. Due to sulfur, here sulfur it is having lone pair, due to lone pair on sulfur. So it undergoes very fast. ఇది ఈ రెండింటిని మనం న్యూక్లియోఫిలిక్ సబ్స్టిట్యూషన్ రియాక్షన్ చేస్తే ఇదేమో NGP జరుగుతుంది, ఇదేమో నార్మల్ SN2 రియాక్షన్ జరుగుతుంది. ఇక్కడ నార్మల్ SN2 NGPలో NGP యొక్క రియాక్టివిటీ చాలా ఎక్కువగా ఉంటుంది, ఇక్కడ 1000 టైమ్స్ ఫాస్టర్గా ఉంటుంది. నెక్స్ట్ దీని మెకానిజం అబ్జర్వ్ చేస్తే దీనిది CH3S CH2Cl మెకానిజం మనం అబ్జర్వ్ చేస్తే ఏం జరుగుతుందో చూద్దాం. ఇక్కడ ఫస్ట్ ఆఫ్ ఆల్ CH3S CH2Cl. Here first of all what happens here, sulfur is having lone pair, this one attacks here, loss of Cl minus takes place, So here this is CH3S CH2, this is here also CH2, here this is having positive charge. Now the attacking of OH minus, this OH minus may attacks here, or this OH minus may attacks here. So this ring open takes place, or otherwise this one ring open takes place. So what we get here, this is CH3S CH2OH, this compound is formed. So here in this one, if you observe, this is internal nucleophilic substitution. First of all, one inversion takes place. This is external SN2, this is one more inversion takes place. The final one is retention of the configuration takes place. In neighboring group participation, retention of the configuration takes place. Here in this one actually there is no inversion, there is no retention. Normally in neighboring group participation, inversion of the configuration takes place. So if we take one more example, sulfur containing compound, by taking 6-membered ring, this is a 6-membered ring. Here we have this is H, this is SCH3, sulfur it is having lone pair, this is H, this is Cl, if it is treated with aqueous 𝗂𝗧. So here mechanism. So with respect to this one, this is alpha, this is beta. Beta carbon is having heteroatom. So what happens in this one? So here this is here H, this is Cl, this is SCH3, sulfur it is having lone pair, this is hydrogen. So here this sulfur internally attacks here, Cl minus, loss of Cl minus takes place. So here this is a neighboring group participation. Here this is here sulfur CH3, here H. Here sulfur is having which charge? Positive charge. Now sulfur got positive charge. This is cyclic trimembered ring is formed. After the formation of cyclic trimembered ring, again here what happens, first of all in this one inversion is taking place, Here Cl and SCH3 both are present in opposite direction, that we need antipositions. After this one, next attacking of OH minus, this OH minus may attacks here, or this OH minus may attacks here. Suppose if it is attacked here, this ring undergoes cleavage. So what we get here, this is here this is H, this is SCH3, here this is H, here it is OH. Here again this is Cl is present below the plane, here OH is also present in the below the plane. ఫస్ట్ ఇన్వర్షన్ జరిగింది, మళ్ళీ ఇన్వర్షన్ జరిగింది. ఓవరాల్గా జరిగింది ఏంటంటే ఓవరాల్గా జరిగింది రిటెన్షన్. అంటే ఒక ప్రోడక్ట్ వచ్చింది ఏంటి, ఇక్కడ సల్ఫర్ CH3H, here it is H and it is OH. Now sir, why OH is attacking here, why OH minus is not attacking here? Suppose if OH minus attacks here, so what happens here? This bond undergoes cleavage, so we get this product. This bond undergoes cleavage na, here we get this is OH, this is H, and here it is SCH3 and this is H. This product is also formed. We get here two products. Here we got two products. One is normal product, another one is abnormal product, SCH3, this is H. This is a neighboring group participation, one reaction. Here in this example, inversion, final retention product. This is a retention product. So that is abnormal product, this is a normal product. In neighboring group participation, two inversions takes place. Final one is retention configuration. So here this is sulfur acting as a nucleophile. In case 1 we are discussed by using nitrogen as a nucleophile, internal nucleophile. That nitrogen acts as a nucleophile. So that is neighboring group participation. Here this is also neighboring group participation. మనం రెండు డిస్కస్ చేసాం, ఒకటి నైట్రోజన్ న్యూక్లియోఫైల్ గా తీసుకున్నాం, ఒకటి సల్ఫర్ న్యూక్లియోఫైల్ గా తీసుకున్నాము. రెండింటిలో కూడా నైబరింగ్ గ్రూప్ పార్టిసిపేషన్. నైబరింగ్ గ్రూప్ పార్టిసిపేషన్లో మనకు కావాల్సింది ఏంటంటే బీటా కార్బన్ దగ్గర హెట్రో ఆటమ్ ఉండాలి. ఇక్కడ బీటా ఆల్ఫా బీటా కార్బన్ దగ్గర హెట్రో ఆటమ్ ఉండాలి. హెట్రో ఆటమ్ పైన లోన్ పేర్ ఉండాలి. ఆ లోన్ పేర్ అనేది ఆ ఇంటర్నల్ న్యూక్లియోఫైల్ మరియు లివింగ్ గ్రూప్ అనేది రెండు కూడా యాంటీ పొజిషన్లో ఉండాలి. అప్పుడు మాత్రమే నైబరింగ్ గ్రూప్ పార్టిసిపేషన్ జరుగుతుంది, లేకపోతే నైబరింగ్ గ్రూప్ పార్టిసిపేషన్ జరగదు. ఇంకొక ఎగ్జాంపుల్ తీసుకోవచ్చు. ఇంకొక ఎగ్జాంపుల్ ఏంటంటే ఇందులో సపోజ్ ఇక్కడ ఏంటి HCH3 తీసుకున్నాం. ఇక్కడ ClSCH3 యాంటీ పొజిషన్లో ఉన్నాయి. ఒకవేళ ClH రెండు కూడా సేమ్ పొజిషన్లో ఉంటే ఏం జరుగుతుంది? సార్ ఇక్కడ సపోజ్ నేను దీన్ని ఏం చేశాను, ఇక్కడ నేను aqueous KOHతో రియాక్ట్ చేశాను, ఇక్కడ కూడా aqueous KOHతో రియాక్ట్ చేశాను, కానీ నైబరింగ్ గ్రూప్ పార్టిసిపేషన్ జరిగింది. ఇక్కడ నైబరింగ్ గ్రూప్ పార్టిసిపేషన్ జరగదు, ఎందుకంటే ఇక్కడ ClSCH3 రెండు కూడా సేమ్ సైడ్ ఉన్నాయి. మనకు కావాల్సింది యాంటీ పొజిషన్. హియర్ NGP does not takes place. NGP does not takes place. Sir, why NGP does not takes place? Why? Because both are present in the same side. So then what happens in this one? Normal SN2 reaction takes place. Normal SN2. Here this is SCH3H. Here it is Cl. This is H. Here it is attacking of OH minus. OH minus is attacking from the back side of the living group. This is normal SN2 reaction takes place. Normal SN2 reaction takes place. Here this is SCH3. This is H. This is here H. Here it is OH. This is SN2 reaction. See, observe these two examples. In neighboring group participation, living group and internal nucleophile must be present in antiposition. Okay, this is neighboring group participation. This is 100% NGP. There is no problem. But here in this case, here SCH3Cl, but both are present in the same side. Both are present at the same side. Therefore, neighboring group participation does not take place. So what happens here? In this one, normal SN2 reaction takes place. That is, general SN2 reaction takes place. In case 3, in this one, pi bond, case 3, this is pi bond acts as a nucleophile, internal nucleophile. This pi bond undergoes neighboring group participation. Here this example, this is a benzene. Here we have CH2Cl. So here this is alpha, beta, gamma. Heteroatom present at beta position or pi bond present at gamma position. This one also possible in neighboring group participation. So here it is treated with aqueous KOH. What happens? Aqueous KOH. Let us discuss that mechanism. This mechanism. So, this is a benzene, next here it is CH2Cl. So, here first of all these pi electrons are migrated to this carbon atom, electron density is more. Next, now it attacking here, then loss of Cl minus takes place, loss of Cl minus takes place. So, here this is double bond, here it is CH2, this is CH2, here this is positive charge. This carbon, this pi bond is shifted from here to here, that means it is losing pi bond, this is losing electrons, therefore, this carbon got which charge, positive charge. After getting this positive charge, now then this is OH minus, attacking of OH minus, attacking of OH minus. This OH minus may attack this carbon or OH minus may attack this carbon. If it attacked here, this pi bond is migrated. If it is attacked here, this pi bond is migrated. So, what happens here? So, this is pi bond, this is pi bond, this is pi bond, here we get CH2, CH2OH, CH2, CH2OH. So, this means this is also neighboring group participation. Neighboring group participation, not only heteroatom, that pi bond also undergoes neighboring group participation. So, this is the product is CH2, CH2OH, CH2, CH2OH, this is a neighboring group participation. And also in case 4, let us discuss, that is case 4. In case 4, oxygen acts as a internal nucleophile. So, what happens here? This is a cyclohexane molecule, here it is OH, this is Cl. OH and Cl both are in antiposition. This is with, suppose if you give numbering 1, 2, this is axial bond, this is also axial bond. One axial to axial, this is a trans, one axial to axial trans. One axial to axial, this is a trans, these are antiposition. Sir, if it is treated with OH minus, what happens here? So, this one here OH minus, this OH minus is subtracting proton, that is O minus, and this is Cl. So, both are in opposite direction, here internal nucleophilic substitution reaction, that is neighboring group participation takes place. Here we get this product, we get in this one that is O minus acting as a nucleophile, and here this is O, and cyclic ether is formed, Oxygen acting as a nucleophile, oxygen neighboring group, oxygen and pi bond, sulfur, nitrogen, all these atoms undergoing neighboring group participation. So, here in this one cyclic compounds we are discussed, in this one pi bond, this is a benzene system also acting as a neighboring group. So, in the previous cases nitrogen and sulfur also acting as a neighboring groups. So, this is a neighboring group participation. So far we are discussed in this class, we are discussing neighboring group participation, it is also important. Remember one point, neighboring group participation is very important. Let us discuss some more examples of some more chemical properties of alkyl halides. So, here this is a RX, here it is treated with NaN3. What happens here? N3 minus is a nucleophile. This one proceeds what, which reaction? SN2 mechanism. So, what we get? This N3 minus attacks from the back side of the leaving group, and this one is eliminated. So, what we get? This is RN3. Here if it is treated with aqueous, that is RO minus. Here what we get? ROR. This is ether is formed. Suppose if it is treated with RS minus, RSR, this is R prime, this is R prime, this is R prime, this is R prime. This one acts as a strong nucleophile, this is also SN2 reaction, this is also SN2 reaction. this thioether is formed. In that reaction, ether is formed. Suppose if it is treated with R prime C double bond O, O minus, R prime C double bond O, O minus. So, what we get here, R O C double bond O, R prime. Here R prime COO minus, it acts as a nucleophile. This one also SN2 reaction, this one also SN2, this one also SN2, this one also SN2. Here all these are strong nucleophiles. Now, see here in this one, suppose if it is treated with dry, so if it is treated with aqueous KOH, already we have discussed that when ROH is formed. So, here in this one, Rx is treated with alkyl halide. If Rx is treated with alkyl halide, this is Rx. Rx is treated with alkyl halide. So, here this is a Woods reaction, Rx. Again it is treated with Rx, that is in the presence of sodium dry ether. Sodium dry ether. Sodium dry ether, this is a Woods reaction. Everybody knows that is what is Woods reaction. So, what we get here? RR. Alkane is formed. If it is treated with RMGX, this RMGX, this is nothing but Grignard's reagent. So, here we get RR. If it is take R prime, R prime. This is a Grignard's reaction, that is a Woods reaction, and also, so this is a SN2 reaction. This is a Williamson synthesis or Williamson synthesis. In Williamson synthesis, what happens? Alkyl halides are treated with sodium or potassium alkoxide or sodium or potassium alkoxide. Sodium or potassium alkoxide. Sodium or potassium alkoxides. It gives ethers. Everybody knows regarding this reaction. So, after this one, let us discuss some more examples. In this one, alkyl halide, if it is treated with dry Ag2O, what happens, and moist Ag2O, what happens? A reaction with dry Ag2O and moist Ag2O. See here, suppose take CH3, CH2Cl. If it is treated with dry Ag2O, dry Ag2O, take one more molecule of Cl, CH2, CH3. This is a dry Ag2O. Here AgCl, here also AgCl, elimination of AgCl takes place. We get CH3, CH2O, CH2, CH3 plus 2 moles of AgCl. This is nothing but diethyl ether. Suppose if this ethyl chloride CH3, CH2Cl, if it is treated with moist Ag2O, here it is a dry condition, that is a dry condition, and this is a moist condition. If it is treated with moist Ag2O moist, here it is having some water, this is converted into alcohol CH3, CH2OH plus AgCl. So, in moist Ag2O, that is Ag2O, first of all reacts with water, it is converted into AgOH, silver hydroxide. In this one, OH minus acting as a nucleophile, that is nucleophilic substitution takes place. This OH minus, here this is CH3, CH2Cl. So, here this one the elimination takes place. What we get? This is CH3, CH2OH. So, this is also nucleophilic substitution, that is also nucleophilic substitution, but it is the condition is here dry Ag2O, that condition is moist Ag2O. In moist Ag2O, alkyl halides are converted into alcohols, dry Ag2O, it is converted into ethers. So far we are discussing that is regarding alkyl halides, that alkyl halides completed, and aryl halides. In alkyl halides we are discussing regarding SN1, SN2, SNI and NGP. In alkyl halides, these four are very important. Aryl halides lo reactions ఏం జరుగుతాయి ఏంటి అనేది డిస్కస్ చేద్దాం. Aryl halides are nothing but this contains halogen is attached to benzene. Here X equal to fluorine, chlorine, bromine, iodine. So, that is if you take this is a fluorobenzene, you take this is a chlorobenzene and here it is bromobenzene and here it is iodobenzene. Alkyl halides undergoes nucleophilic substitution reactions and also elimination reactions. Already elimination reactions we are finished in hydrocarbons. Here in this alkyl halides we are finished, that is nucleophilic substitution reactions. Now in aryl halides we are going to discuss that is nucleophilic substitution reactions. Now you have doubt, sir, in aromatic aryl halides nucleophilic substitution reactions are possible or not? Yes, in aromatic nucleophilic substitution reactions possible and also electrophilic substitution reactions are also possible. Now aryl halides, this aryl halides mainly undergoes two types of reactions. Mainly undergoes two types of reactions. One is aromatic nucleophilic substitution reactions and here aromatic electrophilic substitution reactions. Here generally arenes undergoes electrophilic substitution reactions. This is aromatic electrophilic substitution and this is aromatic nucleophilic substitution reaction. Normal reactions are aromatic electrophilic substitution reaction. These are abnormal reaction. This is aromatic nucleophilic substitution reaction. So where is then aromatic nucleophilic substitution reactions? These aromatic nucleophilic substitution reactions again classified into two types. One is addition elimination mechanism and next one is second one is elimination addition mechanism. Elimination addition reactions, addition elimination reactions. In addition elimination reactions, this is called aromatic SN2 reactions. This is elimination addition reaction, this is nothing but benzene mechanism. Now we are going to discuss that is addition elimination reactions and after that one elimination addition reactions. So this is aromatic nucleophilic substitution reactions. In aromatic nucleophilic substitution reaction, the first one is addition elimination reactions. So in addition elimination reactions, what happens? First of all, nucleophile is added to the benzene ring, that means haloarene, that means addition takes place. After the addition of nucleophile, the loss of Cl minus or X minus takes place, that is called addition elimination reaction. So now, here we are taking one example. Here this is a chlorobenzene, this is a para-nitrochlorobenzene. This para-nitrochlorobenzene, if it is treated with 𝗘𝗿H, aqueous 𝗘𝗿H, what happens? Here we get this is Cl is replaced by OH, that is para-nitrophenol is formed. This is para-nitrochlorobenzene. This is what we get here, para-nitrophenol is formed. Here this is a nucleophilic substitution reaction. Here the mechanism, if you observe the mechanism, what happens here? This is a chlorobenzene, this is a nitro group. Here OH minus, it is a nucleophile, OH minus is a nucleophile. So this nucleophile attacks at this carbon and the pi electrons are migrated towards carbon. So here this is Cl and here this is OH and here it is negative charge, OH and negative charge. Here double bond and here also double bond, this is N double bond O minus, here it is plus. Now after the formation of this carbon ion, this one migration takes place and the pi electrons are migrated here. This is a slow step and it is a rate determining step. It is a slow step and rate determining step. This reaction is also, if you observe this reaction is also just like aromatic electrophilic substitution reaction. In aromatic electrophilic substitution reaction, the first step, that is a formation of carbocation, formation of sigma complex, is a slow step. Here also this is called sigma complex, this is also called sigma complex, but there carbocation is formed, here carbanion is formed, that is called cyclohexadinyl cation in that reaction, but in this reaction this is called cyclohexadinyl anion, and that is also stabilized by resonance, this is also stabilized by resonance. So what we get here? This one, in this one, here double bond, here double bond, here it is Cl here it is OH, this is N double bond O minus, here it is plus, here negative charge. After the formation of this negative charge, again this negative charge is migrated here, the pi electrons are migrated here. So, now this is double bond, here it is negative charge, here it is Cl, here it is OH, this is N double bond O plus. If you observe this one, if you observe these structures, negative charge here this carbon atom and this carbon atom and this carbon atom, again delocalization, again here to there, then there to here, delocalization is taking place. So, we can write this structure like this, how this is here, this is Cl, this is OH, this is Cl, this is OH, and here like this is negative charge, this is NO2, and this is called sigma complex, this is called Mädchen-Hammer complex, this is Mädchen-Hammer complex. Whereas in aromatic electrophilic substitution reaction we call that is a Wieland complex. Here this we call this is a Mädchen-Hammer complex, that is a carbocation, this is a carbanion, that is called sigma complex, this is also called sigma complex. Here in this one, here NO2 group is present at para position. So, what is happening, sir? Here we get one more resonating structure, this negative charge may migrate here, this one here we get one more resonating structure, this is the resonating structure. Here double bond N, here it is O minus, here it is O minus, this is plus, here this is Cl, this is OH, this is Cl, this is OH. If you observe this structure, this is the most stable structure, this is a most stable structure. Sir, why you are calling this is a most stable resonating structure? Why? Because in this structure oxygen having negative charge and all atoms having octet electronic configuration, So, that means this is more stable. So, what is the meaning of this one? Means if NO2 is an electron withdrawing group, this NO2 is an electron withdrawing group. If electron withdrawing group, if it is present at ortho and para position, here in this one we are observing that is this it is present at para position. This NO2 it is stabilizes, if NO2 is present at para position, the carbon ion is stabilized. ఒకవేళ NO2 కానీ ఎలక్ట్రాన్ విత్డ్రాయింగ్ గ్రూప్ కానీ పారా పొజిషన్లో ఉంటే నెగిటివ్ ఛార్జ్ అనేది స్టెబిలైజ్ అవుతుంది. కాబట్టి electron withdrawing groups, that means electron withdrawing groups, if these are present at ortho and para positions, it increases the rate of what aromatic nucleophilic substitution reaction. And one more point, as the number of electron withdrawing groups increases at ortho and para positions, rate of aromatic nucleophilic substitution reactions increases. Here electron withdrawing group it is at a para position, this is a sigma complex. Suppose if it is present at ortho position, there also carbanion is formed, that is also stabilized by NO2 group. Suppose if it is present at meta position, the negative charge is not stabilized by NO2 group. If NO2 group is present at ortho position, what happens? Let us discuss that one also. Ortho nitrochlorobenzene. Here it is treated with aqueous KOH. Here it is heating, that is also heating. So, what happens here? This is OH NO2, orthonitrophenol. Now, see here the mechanism, this mechanism. Here again same, this is Cl, here it is NO2, that is OH minus is attacking here, the pi electrons are migrated. So, here this is Cl, this is OH, here it is NO2, here negative charge, double bond. Again this one it is a slow step and it is a rate determining step, The negative charge is stabilized by resonance, delocalization of electrons. Here double bond, negative charge, double bond, here it is NO2, this is Cl, this is OH. Again, here this negative charge is migrated here, the pi electrons are migrated. So, we get, so this is here it is double bond, here it is NO2, here it is negative, this is Cl, this is OH. If you observe this one, the negative charge is carbon here and here and here. That means, so the negative charge is oscillated between these carbons. This is negative and this is Cl, this is OH, this is NO2. This is called sigma complex. This is also called Meitner-Hamer complex. So, what is the specialty of this one? Again, here it is having one more resonating structure. This is NO2, N double bond O minus, here it is plus charge. The negative charge is migrated here, the pi electrons are migrated here. So, we get this structure, this is double bond, here it is Cl, this is OH, here double bond N, O minus, here also O minus. Here negative charge, here it is present at ortho position. The carbon ion is stabilized by electron withdrawing group, and this is more stable structure. In all atoms having octet electronic configuration, oxygen is also having negative charge. That means, if nucleophile, if attached, so that means not nucleophile, electron withdrawing group, if it is present at ortho and para position, that is the carbon ion that is stabilized by resonance. Therefore, electron withdrawing groups at ortho and para position increases the rate of reaction towards aromatic nucleophilic substitution reactions. Here, suppose if it is present at meta position, what happens, that we also discussed. And one more point here, as the number of electron withdrawing groups, increases at ortho and para position, rate increases towards aromatic nucleophilic substitution reactions. So, example, suppose this is ortho nitrochlorobenzene, here one electron withdrawing group, here we have two electron withdrawing groups, and here we have three electron withdrawing groups. Here we have 3 electron withdrawing groups. Here 3 electron withdrawing groups, therefore, this is more reactive. So, this first one is less reactive than second one is less reactive than third one. This is more reactive. Suppose if it is treated with 𝗂H, it requires high temperature and high pressure. So, what we get here? This is OH, Cl is replaced by OH and orthonitrophenol is formed. Suppose if it is treated with 𝗂H, it requires here also high temperature, and also pressure. Here when compared to this one, suppose if it requires 300, it requires 200 degrees Celsius. Here temperature is more and pressure is also more, here temperature is not that much more and pressure is also not that much high pressure. So, due to presence of 3 electron withdrawing groups, what we get, this is OH, this is NO2 and it is NO2. If you observe this one, just by adding of water at room temperature or just slightly heating, what happens, this Cl is replaced by OH, this is a OH and here it is NO2 and this is also NO2, this is also NO2. This is called picric acid is formed, picric acid is formed. So, if we observe this one, 1 NO2, 2 NO2, 3 NO2. 3 electron withdrawing groups ఉన్నాయి కాబట్టి ఇది వాటర్ తోనే రియాక్ట్ చేయగానే సింపుల్ గా HCl వెళ్ళిపోయి OH వచ్చేసింది. This is called picric acid. The specialty of picric acid is it is an acid which do not contain COH. That is one specialty. And this is a picric acid when it is treated with sodium bicarbonate. It liberates carbon dioxide gas. Whereas phenol plus sodium bicarbonate, carbon dioxide is not liberated. The acidic nature of picric acid, it is approximately equal to carboxylic acid. Here it liberates carbon dioxide when it is treated with sodium bicarbonate. Now, suppose if NO2 group is present at meta position, what happens? Cl, NO2. Here it is treated with 𝗘𝗽H, aqueous 𝗘𝗽H heating, Cl is replaced by OH, Cl is replaced by OH, this is NO2. Now, let us discuss that mechanism. Cl, this is a benzene, it is a Cl, this is NO2, here OH minus, here it acts here, the pi electrons are migrated here. So, this here, this is Cl, here negative charge, double bond, here it is NO2. And it is stabilized by resonance, negative charge is migrated here, pi electrons are migrated here. So, in this one, this is a here double bond, NO2, here it is Cl, here this is Cl, here it is we have OH, this is also here it is OH, this is negative charge. Again one more resonating structure, here one more resonating structure, double bond, negative charge, Cl, OH, NO2. If you observe these resonating structures, here negative charge is not stabilized. In the previous case, if NO2 is present at ortho and para position, NO2 stabilizes carbanion. We have one more resonating structure there, here is now other resonating structures. This is not having other extra stability, just it is NO2 if it is present at meta position, just it is having only inductive effect. Whereas that if NO2 is present at ortho and para position, we have resonance effect, here it is having only inductive effect. So, here this one also okay, but it requires some high temperature and pressure required condition. Suppose if you write the resonating structure of this one, that is sigma complex, here this is Cl, this is OH, this is negative charge, and this is what? This is NO2. This is metachloronitrobenzene, which is treated with 𝗘𝗽H, we get with metanitrophenol. So, after metanitrophenol, so next, so after this electron withdrawing groups and electron releasing groups, suppose not only OH minus, suppose if we have CN groups or other groups, what happens? So, if we take this example, here we have two Cl groups, this is NO2, here Cl, here also Cl. If it is treated with KCN, here one equivalence of KCN. Now, our question is which Cl is replaced, either this Cl or this Cl. With respect to Cl, NO2 is present at meta position, NO2 works at ortho and para position. This Cl is replaced, not this Cl. So, here we get the compound is, this is NO2, here it is Cn, here it is Cl, Cn and Cl. Suppose if it is treated with excess of KCN, so what happens here? This is NO2, here it is Cn, this is Cn. In the previous examples we have discussed that is Cl minus is replaced by OH minus, but here this Cl minus are replaced by Cn. Suppose if you take one equivalence, this Cl is replaced, not this Cl. If you take excess Cn, both Cls are replaced by Cn. So, after this one, suppose fluorobenzene, chlorobenzene, bromobenzene and iodobenzene, which is more reactive towards nucleophilic substitution reaction. So, take this is a fluorobenzene and take chlorobenzene and take bromobenzene and take iodobenzene. Fluoro, chloro, bromo and iodobenzene, which is more reactive towards aromatic nucleophilic substitution reaction. Actually, aromatic nucleophilic substitution reaction, so the close step is a rate determining step, mainly that depends on CX bond polarity, and the second one is size of the halogen atom. Here in this one, CF, F electronegativity is more when compared to Cl, Cl is more than bromine, bromine is more than iodine. In the electronegativity difference is more here and polarity is more here when compared to CF, CCl, CBr, Ci, CF polarity is more, and here this fluorine withdraws more electrons. What happens here? Electron density decreases, therefore nucleophile easily attacks, therefore fluorobenzene is more reactive than chlorobenzene, chlorobenzene is more reactive than bromobenzene, bromobenzene is more reactive than iodobenzene. This is a rate towards, this is a reaction or rate towards aromatic nucleophilic substitution, aromatic nucleophilic substitution. So, fluorobenzene is more reactive than chlorobenzene, chlorobenzene is more reactive than bromobenzene, bromobenzene is more reactive than iodobenzene. After aromatic nucleophilic substitution reaction and aromatic electrophilic substitution reactions, that is chlorobenzene, it also undergoes aromatic electrophilic substitution reaction. So, that is aromatic electrophilic substitution reactions of chlorobenzene. This is a chlorobenzene aromatic electrophilic. So, here chlorobenzene, this if you observe this chlorobenzene, this is a chlorobenzene. This chlorobenzene, chlorine is having lone pairs. Here chlorine, it is having two types of effects, one is minus inductive effect and plus resonance effect, plus resonance effect. This minus inductive effect, it operates, inductive effect operates reactivity, whereas resonance effect operates orientation. Due to resonance structure, electron density increases at ortho and para position, whereas inductive effect, this inductive effect controls reactivity. Here, due to resonance effect, electron density increases at ortho and para position, therefore, it is a ortho and para director towards electrophiles. It is a ring deactivating group, it is a Cl is a ring deactivating group, but it is a ortho para director. That means chlorobenzene, if we compare chlorobenzene and benzene, which is more reactive towards electrophilic substitution reaction. That means here, so evarina adigithe chlorobenzene is less reactive than benzene. Why? Because Cl, it is having minus inductive effect. That minus inductive effect controls reactivity. This is less reactive when compared to benzene. Chlorobenzene is less reactive towards electrophilic substitution reaction when compared to benzene. This Cl, it is having, this is called weakly deactivating group, but it is which director? It is a ortho para director. It is a ortho para director. So now let us discuss, that is aromatic electrophilic substitution reactions of chlorobenzene. First of all, let us write the that is resonating structures of chlorobenzene. Resonating structures of chlorobenzene. This is a chlorobenzene. Here it is a chlorobenzene. Chlorobenzene, chlorine is having lone pair. Here the electron pairs are migrated towards carbon, and here it is an electron plus resonance effect. Here this is double bond Cl, it is plus, it is minus, here double bond negative charge in migration. So here these are the resonating structures, double bond negative charge, here double bond Cl, here it is plus, again this negative charge, again here the pi electrons are migrated towards carbon. This is double bond, here it is negative charge, this is double bond Cl plus, again negative charge is migrated, that pi electrons are migrated towards chlorine. Here we get this is a Cl, this is double bond, this is a chlorobenzene. So if you observe this resonating structure, the negative charge is present at ortho para ortho, that means it is a ortho para director, it is a ortho para director. It is a ortho para director. If electrophile approaches towards chlorobenzene, what happens? That electrophile attacks at ortho and para position. So in this chlorobenzene, that is new electrophile never attacks at meta position. Suppose if chlorobenzene, if it is treated with halogenation, here this is a chlorobenzene, here it is treated with Cl2 in the presence of AlCl3. What happens? This Cl2 reacts with AlCl3, it gives AlCl4 minus plus Cl plus. If the electrophile is Cl plus, this is an electrophile. So this is nothing but this is called chloronium electrophile. This is called chloronium electrophile. This chloronium electrophile attacks at which position? At ortho and ortho para position. It is a ortho para director. Now it attacks at which position? At ortho position. This is ortho dichlorobenzene, and one more is para dichlorobenzene. Ortho dichlorobenzene and para dichlorobenzene. para-dichlorobenzene is a major and ortho-dichlorobenzene is a minor. So, this is a major, and here due to steric hindrance this is a minor, that is a major. Suppose if it is subjected to nitration of chlorobenzene, nitration of chlorobenzene. Chlorobenzene, when it is treated with nitration mixture, concentrated HNO3 plus concentrated H2SO4 at what ratio? 1:1 ratio. Here nitration takes place at which position? That is on heating. Here orthonitrochlorobenzene and para-nitrochlorobenzene, orthonitrochlorobenzene and para-nitrochlorobenzene. Here in this one, in nitration mixture, that is HNO3, HO, N double bond O, here this is O minus, here it is plus, and H2SO4, HO, S double bond O, OH. Here oxygen is having lone pair, here protonation takes place. So, now this is HOH, here it is plus, here it is N double bond O minus, here it is plus, then O minus, S double bond O, OH. Then here negative charge is migrated, here loss of water molecule takes place, water molecule and NO2 plus electrophile and HSO4 minus. This is NO2 plus electrophile is formed. Here in aromatic electrophilic substitution reaction, this one takes place in mainly two steps, that is formation of sigma complex and loss of H plus. Formation of sigma complex, generally it is a rate determining step. So, here in this one, in nitration mixture, NO2 plus electrophile is formed. Here in this reaction actually HNO3 is acid and H2SO4 is also acid, but in nitration mixture this H2SO4 acts as a acid and HNO3 acts as a base. Here chlorobenzene, this chlorobenzene, when it is treated with concentrated sulfuric acid on heating, here we get here the electrophile is SO3H as electrophile, that one attacks at ortho position and also this one attacks at para position also. This is ClSO3H. This is a sulfonation, this is also aromatic electrophilic substitution reaction. In this one the electrophile is, electrophile is SO3, in this one the reaction electrophile is SO3. So, after this one, this is a sulfonation. After sulfonation, next one here this chlorobenzene undergoes different types of reaction. Suppose Friedel-Crafts alkylation, Friedel-Crafts reaction. So, here chlorobenzene, this chlorobenzene, when it is treated with CH3Cl in the presence of AlCl3, here alkylation takes place at ortho position as well as at para position. This is a para-chlorotoluene and this is a orthochlorotoluene, two compounds are formed. So, if similarly if it is treated with Friedel-Crafts acylation CH3 C double bond O Cl in the presence of AlCl3, here acylation takes place at which position? At ortho position as well as at para position, So, this is Friedel-Crafts alkylation and Friedel-Crafts acylation, and also chlorobenzene, it also undergoes some other reaction that is called �𝗏-Fittig reaction. This chlorobenzene, it is treated with sodium dry ether, we get biphenyls, this is a biphenyl, this reaction is called �𝗏-Fittig reaction, and also Fittig reaction. One more is Fittig reaction, one is �𝗏-Fittig reaction, another one is Fittig reaction. In �𝗏-Fittig reaction, here this chlorobenzene, it is treated with CH3Cl and sodium dry ether, we get biphenyls plus we get byproduct, this is CH3 plus also CH3. This is a �𝗏-Fittig reaction, and Fittig reaction is nothing but chlorobenzene, when it is treated with sodium dry ether, we get biphenyls, only biphenyls are formed, the remaining reaction, that is biphenyls and toluene, and so this is a �𝗏-Fittig reaction, this is a Fittig reaction. In Wurzburg reaction, aryl halides plus alkyl halides in the presence of sodium diether, it gives biphenyl plus toluene. In Fittig reaction, chlorobenzene plus sodium diether, it gives biphenyl. This is called Fittig reaction. Actually, in aryl halides undergoes electrophilic substitution reactions and aromatic nucleophilic substitution reaction. So far, we are discussed that is aromatic electrophilic substitution reaction, and also we are completed, that is aromatic nucleophilic substitution reactions.